Hello everyone, today I will briefly present my M5 Practice Hackthon project. This project uses the tele-customer churn dataset to predict whether a customer would churn, while also applying the responsible AI principles, including fairness analysis, interpretability, and aesthetical reflection. First, I cleaned and prepared the data. The data set contains nearly thousands of records, and the target variable is churn. So the overall churn rate is about 26.54%, which means it's an imbalanced binary classification problem. Were also 11 missing values in total charges, and I handled them in pre-processing pipeline. If we look at the anomaly deduction chart, the box plot titled the uh, monthly charges by outlier flag shows that outlier cases tend to have higher monthly charges, but their churn rate is actually lower than non-outliers. This suggests that the outliers are unusual, but not necessarily highest risk churn customers. So I kept them in the analysis instead of removing them. Next, for model development, I compared three classical machine learning models: logistic regression, random forest, XGBoost. In the model comparison table, logistic regression achieved the best validation, ROC and AUC, around 0.836. So I selected this as my final model. This choice was not only based on the performance but also on the interpretability, because logistic regression is easier to explain and better allied with responsible AI principles such as transparency and accountability. Then I examined the shareholder optimization chart. In this figure, the blue line uh, represents the F1, and the orange line represents recall. The green line represents the precision, and the red dashed line marks the selected sharehold of 0.51. The chart shows that when the sharehold is too low, recall is high but precision is weaker. When the sharehold becomes too high, precision improves, but recall drops sharply. Since missing a true churner is more costly in a churn prediction setting, I selected 0.51 to maintain a better balance between recall and precision. On the test set, the final model achieved the ROC of 0.8418 and a pure AUC of 0.6317, an accuracy of 0.7473, a recall of 0.7701, and an F1 score of 0.618. If we look at the confusion matrix, so the model correctly identified 288 true churners at the same time. 86 churners were missed, and 270 non-churners were incorrectly predicted as churners. This tells us that the model is responsibly effective at capturing churn risk, especially because the recall is fairly high, but it also produced some false positives, which could lead to unnecessary intervention costs. Now I want to focus on fairness, which is one of the most important responsible AI components in this project. I evaluated the fairness across two sensitive attributions, gender and senior citizens. In the fairness by gender table, the selection rate, accuracy record, and F1 are very similar to for the female and male customers. The demographic party difference is only 0.0026, and the equalized odds difference is only 0.0189. This suggests that the model behaves quite consistently across genders, with no strong evidence of gender bias. However, fairness by senior citizen table tells that a different story. The selection rate differs substantially between non-senior and senior customers, and about 0.347 versus 0.658. The demographic party difference is 0.3106, and equalized odds difference is 0.235. This indicates a much more noticeable disparity between senior and non-senior groups, which is main fairness concern identified in my analysis. The next is interpretability. If we look at the deep learning feature importance chart, tenure is clearly the most important feature, and it stands out far above the others. The next most important features are total charges, contract 2-year, monthly charges, and internet service fiber optic. This is consistent with business intuition because customers with shorter tenure and less stable contracts are generally more likely to churn. If we look at the SHAP summary plot and the SHAP bar plot, we see a similar pattern in the classical model. Tenure, total charges, and monthly charges are again the top drivers. The SHAP summary plots also help interpret the direction. For example, lower tenure tends to push the predictions more strongly towards the churn, while higher monthly charges also increase the churn risk. So SHAP tells us not only which features matter, but also how they influence the prediction. The local SHAP waterfall plots the plot and the LIME explanation both focus on one individual customer. The waterfall chart shows the tenure, monthly charges, and the contract 2-year strongly influence the customer's prediction, and the LIME chart shows a similar pattern. This consistency between global and local explanations increases confidence that the model is learning meaningful patterns rather than random noise. Finally, the partial dependence plot. The partial dependence plot provides another way to interpret the model. The left plot shows that as tenure increased, the predicted churn probability decreased sharply, and the right plot shows that as monthly charges increase, churn risk generally rises. This plot visually confirms the same message we saw from SHAP and feature importance, which makes the interpretation more reliable. In conclusion, this project not only produced a solid churn prediction model, but also demonstrate how responsible AI principles can be integrated into machine learning workflow. The model appears relatively fair across gender, but shows a more noticeable disparity for senior citizen group. At the same time, SHAP LIME feature importance and PDP consistently show the tenure charges. And the contract related variables are the key predictors. So value of this project is not only predictive performance, but also the balance between performance, fairness, and interpretability. That's all. Thank you for listening.